Hi everybody. I'm going to talk today a bit about an application of Fourier analysis, which is to sound. So first of all, before we get into that, we should talk about what is sound. So sound is a wave. Hopefully that is familiar. And it's a wave. What is it a wave of? It's a wave in the air. So basically you're compressing and you're causing a compression wave, a disturbance which travels through the air. And as that travels onward, eventually it will hit your ear, and your ear has an eardrum which will vibrate, and the vibrations are then interpreted by your brain as sound. So that's a sound wave it's a disturbance traveling through the air, and then it hits your ear and your brain interprets it as sound. Maybe I can help you visualize that by taking a look at a little simulation here. So here we have a visualization of a disturbance in the air of a sound wave. So let me try to play it here. And the green molecules are supposed to be air molecules. This is, for example, a disturbance of air in a pipe. So for example, if you sort of vibrate the air at one end of the pipe, this is what will be going on inside of the pipe. So the green ones are all air molecules, and the red ones are just particular air molecules, so you can watch and see that it is an oscillation, that those molecules are moving just back and forth. The blue dashed line there is it's kind of to help you visualize. So that you can kind of visualize that as a graph of density or compression of the air, or pressure. I guess pressure is best. So when the area, let me pause it for a moment. In this area right here, you can see that the air is compressed, and so the pressure there will be the highest, and that's the maximum of the wave, right? And then this area here, the air is kind of spread out more than normal, so we call it rarefied, and that means that that will be the minimum of the wave. And as this wave travels forward, you can see that this part here, which is at a maximum of compression, will later be at a minimum, because this part of the wave will travel there. So maybe I can just play it a little bit more. And then we can adjust the frequency of the wave. So if I make the wave higher frequency, that will cause the oscillations to be faster. So there's the frequency. And we can also adjust the amplitude of the wave. So the amplitude of a wave will change the oscillation. So I'm decreasing the amplitude now, and that makes the oscillations smaller. So amplitudes are like bigger oscillations of the air molecules, and frequency is how fast are the air molecules moving back and forth. There's also wave speed, so I can change the speed at which the wave is traveling through the air. And you can see that then these crests are traveling faster to the right. So hopefully that helps you to visualize an sound wave. Okay, now let's talk a bit about instruments. So we understand what a sound wave is, but how do you create one? You disturb the air, so you vibrate it somehow. So when I'm talking, my vocal cords are vibrating, and they're causing the disturbance of the air, which propagates outward. And if you were in the same room as me, that disturbance would travel to you, and you would hear it. It would go to your ear, and you would interpret it as sound. So let's talk a bit about musical instruments. Same thing is done with musical instruments. So for example, if you take a tuning fork, I don't have one with me, but if you take a tuning fork and you hit it, it vibrates. The two tines of the tuning fork vibrate, and that vibration disturbs the air, and that disturbance travels outward, and you hear it as sound. Now, let's make a little bit of a correspondence between what exactly we're hearing and the frequency and the amplitude of the wave. All right, so when it comes to sound, the frequency of the sound corresponds to the pitch. So a high-pitched sound has a high frequency. The air molecules are vibrating, oscillating faster back and forth. And the amplitude of the sound corresponds to the intensity or the loudness. Okay, so if I increase the amplitude of the oscillations, I will hear a louder sound. If I change the frequency, I will be changing the pitch. Okay, and hopefully that's... So let's talk a bit about music. For those of you who don't know, if you haven't played an instrument, the pitch of the sound is usually given a note. So for example, the note A, sometimes written as 440, is a pitch, is a sound pitch with frequency 440 hertz. And that is just a note that I'm picking arbitrarily because that note is the one that they use to tune an orchestra. So at the beginning, if you see an orchestra concert, someone will play an A, and then everybody else will tune their instruments so that when they play an A, it's the same frequency as the instrument that first played, so that your orchestra is all kind of in tune. Now the big question, which I want to answer in this lecture, is the following. So those of you who play a musical instrument maybe know this. If I play the note A on the piano, and one of you maybe is playing the guitar, and you play the same note, you play the note A, those clearly sound different. In that, I mean, you can tell that a piano sounds different than a guitar. That's what gives the different instruments their character. So the big question is, why do different instruments sound different when they're playing the same note? And for that answer, that will lead us to Fourier series. And so we're going to try to answer that question. So to get started, I'm going to focus, as a concrete example, I'm going to focus on a string instrument. Let's focus on a string instrument. And for example, a guitar or a violin. And you can think about a string instrument as being very simply modeled as, it's just a string which is fixed at both ends. So there's a string here, and it will be attached at two ends of something, and the length of the string will be L. Now, so how does it, for example, a guitar work? You pluck the string vibrates in a certain way, and that vibration disturbs the air in a certain way, and that causes the sound wave to travel outwards, and then you hear the sound wave. And I want to think about some special ways that the string could vibrate. So here's one of them. So I'm going to have the ends are going to be fixed, they're attached. And one way that you could specially vibrate this string would be so that the wavelength, one way you could specially vibrate this string is so that the wavelength is actually twice this L. Okay, so you could have a vibration that looks like this. This is what we call standing wave, which maybe you guys have seen before. And this has wavelength equal to 2L. Okay. In case it's not clear, what I'm drawing here is the string at two different times. So at some time the string is like at the top bowed upwards, and at some other time the string is bowed downwards, and it's moving up and down just as one, like this, like a jump rope, going up and down. And the reason why the wavelength is 2L is because if you think about extending if it's forming a perfect sine wave, if I extended it out like that, the wavelength would be from here to here, which would be 2L. Okay. Right. So this is what we call the fundamental mode. So we call this fundamental mode. It's a fundamental mode of oscillation. And we usually label it with a number, n equals to 1. And the question is, if the string was to vibrate in this way, what sound would you hear? Well, we know the wavelength. Lambda is 2L. And hopefully you also maybe remember from previous classes that the wavelength times the frequency is equal to the speed of the wave. And the speed is fixed by the properties of the string. You may remember this formula. V is the square root of tension divided by the mass density of the string. That's why when you are tuning a guitar, you're tightening it or loosening it. You're changing the tension. That's changing the speed of the wave. The wavelength is fixed because the length of the guitar is fixed, so then it changes the frequency that you hear. So let's think about what frequency would I hear if the string oscillated in this pattern. Well, easy enough, right? F, and I'm going to call it F1 because it's n equals to 1 here. F1 is the speed divided by the wavelength, and the wavelength is 2L, so it's V divided by 2L. That would be the frequency that I heard. So maybe, for example, if you're tuning your instrument in the beginning of an orchestra concert, we could say maybe this is 440 hertz as an example. So that's one way that if I could get the string to oscillate in this particular way, so in this nice jump rope kind of pattern, I would hear a pure tone of 440 hertz. That's the claim. Okay? But there are other ways the string can oscillate. For example, we could get the string to oscillate this way. So I would have the ends of the string like this, and then I can have my string oscillating like this, right? This is still L. And in this case, the wavelength of the string, which is the distance over which it repeats, is equal to L. So if the string oscillated in this pattern, what frequency would I hear? We call this n equals to 2. And so the frequency that I would hear would be V divided by lambda. And V divided by lambda is just equal to L in this case. And hopefully you can get the idea how this works, that I could then put one which has n equals to 3 and n equals to 4. By the way, I should maybe explain what is n. N is the number of these maximum points of oscillation. We call these antinodes. The nodes are the places which don't oscillate at all. So these things are nodes. So the edges are the nodes. The middle is a node in this case. And then the places halfway between the nodes are antinodes. If I have two antinodes, that's n equals to 2. If I go back up here I have one antinode, which is right in the middle there. And that's n equals to 1. So if the string oscillates in the pattern with n antinodes, the frequency that you would hear would be Fn turns out to be Nv divided by 2L. Okay, so and you can check that that agrees with these here. If n is equal to 1, I get this formula. If n is equal to 2, I get this formula. It would be quite hard to get the string to oscillate in this nice pattern. So if I just grab the string and I pluck it and I just listen to what comes out, it's not going to be this nice sine wave. So what if I set up a more kind of general oscillation, something which is kind of messy, you know, maybe something like this, I'm just gonna draw something, you know, maybe it's messy, it's got a messy pattern like this. So the string is oscillating in this way. That's not a pure sine wave. It's not n equals to 1, it's not n equals to 2. So what sound would you hear? The amazing claim is that this most general oscillation here, where this distance is L, is a combination of these, right? Of the n equals 1 and the n equals 2. So it's just some combination of those other sounds. The general oscillation is a combination of n equals to 1 mode, n equals to 2 mode, n equals to 3, and so on, etc. So any kind of oscillation of this string can be written as a combination of these other ones, these nicely behaved ones. And that means that the sound that you hear, which comes out of this here, is really, you're hearing all of those sounds at once, the n equals 1 frequency, the n equals 2 frequency, the n equals 3 frequency. You're hearing all of those at once. So this sound is a combination. In the case of the example I did above, I said it's a combination of 440 hertz, so you're hearing that frequency, but then n equals to 2, you'd have 880 hertz as well. And then, let's see, 440 times 3, what is that? 1320? And so on. Which combination so if I pluck a violin string, how much of that sound is 440 hertz? How much of that sound is 880? How much of that sound is 1320? You can probably see where this is going. For this, you need a Fourier series or Fourier analysis. Fourier analysis will tell you. So if I could write this function of this sort of messy oscillation as a Fourier series, it would tell me how much of the n equals 1 frequency is in there, how much of the n equals 2 frequency is in there, and so on. And so every instrument has a different Fourier series. Every instrument has a different combination of sounds. They're all playing the same fundamental note, but they have different mixtures of all of the higher, what they call harmonics. These are called harmonics, n equals 1, n equals 2 harmonics. And so that's why different instruments sound differently, because they have different combinations of harmonics. So that's the kind of major point I want you to take away, is that each instrument sounds different because they have, or I should say they create a different combination of those sounds of, 440 hertz, 880 hertz, 1320 hertz. So that's a really amazing fact that, the sound played on a violin, it sounds so rich and sort of beautiful and complex. It's actually made up of simple things, simple pure frequencies, and the particular combination is what gives the violin its sound. And if I take those same frequencies and take a different combination, I can hear a different instrument, which is like a trumpet or a clarinet. All right, so in class, I will try to do some demonstrations of this, and we'll try to go a little bit further with the analysis. So I'll try in class to show you the waveforms of some instruments, and you can kind of get an idea of how it compares to the pure tone and why the different instruments sound differently. And then we'll start to do some analysis and problem solving on this topic. So I hope you've enjoyed this lecture. I did post a second video which I'd like you to watch, which is only 6 minutes long, and it deals with the same topic, and it's a bit old, so you might find it amusing, but it is from The Nature of Things by Ken Suzuki, but it's clearly many decades old. But it's a nice video which illustrates some of the main points that I'm covering here. So I'd ask you to also watch that before class. See you all in class. Bye-bye.